Hi everyone, welcome to one more ALAG webinar. I'm very excited to have you today for one more ALAG webinar focused on analytical geochemistry. The ALAG webinars are sponsored by Nova Analytica, Thermo, Sense, and Faperge. In name of ALAG, we are very grateful for them to enable this fantastic event. In addition, I warm thank to all the organized committee, especially for Vinicio, Laercio, and Luisa, our junior directors that work every webinar on backstage to work hard and provide us this first-rate program. Before moving to our talking, I have a special offer to you. Become a LAG member, affiliate today and help this great society become stronger and stronger. Soon we will offer special courses and affiliate members will have a special discount to do this. So hurry up and become an Alago member. Our talk today is about a new technique, a new methodology to analyze NSO compounds, the FT-ICR MS. And you have a great pleasure to have here today Laercio.
Thank you, Boniek.
In 2010, a Master of Science in Petroleum Reservoir and Exploration Engineer measuring petroleum geochemistry for the North Fluminense State University in 2013, and a PhD in Petroleum Reservoir and Exploration Engineer measuring in petroleum geochemistry, also from UENF in 2016. He was a professor of the ONG Brazilian Industrial Mobilization Program in 2013 and the Municipal University of Macaé in 2016 until 2017. In 2018 2019, he spent a year as a postdoctoral research in organic geochemistry at GFZ, German Research Center of Geoscience, Potsdam, Germany. Besides 2013, he's a geochemist at the Laboratory of Petroleum Geochemistry, George Triggs, of the LENEP UENF, working as technical manager, researching projects on organic and petroleum geochemistry, and advising undergrads and graduate students. Currently, he is also part of the board of junior directors of the Latin American Association of Organic Geochemistry, ALAGO. Laercio, welcome to ALAGO webinar, and you have, it is your turn.
Thank you, Professor Boniek. Thank you for the Alago for the invitation. So I will open my presentation. So thank you for the Alago to invite me. I was honored for that. So it's really good to be here today to share a little bit about this topic that I'm always very, very interested of. That is the application of the ultra-high resolution FT-ICR MS to assess the positional paleoenvironment of black shales and crude oil source rock. So, where is the target of this presentation? Is to show the significance of NSO compounds assessed by FT-ICR MS to reconstruct the paleoenvironmentals. So, for that, we need to understand a little bit about the methodology, about how the equipment works. So, I will give you an overview about it. So, at first, we have the samples. In the case of this webinar, we have the oil samples, the complex samples. We have the oil sample, and that could be a produced crude oil or some oil extracted from some reservoir rock. And we can also have, 1 minute, let me put the laser. And we also can have the extracts, the organic extract from source rocks that generate the petroleum, or black shale. What is black shale? Black shale is a fine-grained shale that usually have high content of organic matter and normally high content of sulfur. And sometimes the black shale are also source rocks that generate petroleum. So we have the sample. Then we need the source, the ion source, because to analyze in the FT-ICR MS, you need the species as ionized. So in the case of this presentation, I will focus on the electrospray ionization that is suitable for NSO polar compounds. So what we want is to generate quasi-molecular ions, protonated or deprotonated. So after generate the ion, we have the ion cyclotron resonance mass spectrometer. Here, what we have is a magnetic field. It's refrigerated magnetic. So what happens here is that the ion is in a circular orbit. So, and what is measured is the ion's frequency oscillation that is related to the mass of the ions of the species that we are assessing. So from these masses, in the end, we have the mass spectrum, as we can see here. But the thing is, we have usually a very complex mass spectrum. So what we do, for example, we have this example from the Smith and collaborator 2018 that found more than 4,900,000 compounds detected in a heavy petroleum distillate by 211 Tesla FT-ICR MS. This 211 Tesla is the equipment with the high resolution that we have today. So from this mass spectrum, we need at first do the assignment of the molecular formula, because we only have the mass, but the mass is very accurate. So we can, from that, achieve the molecular formula. And then after that, we need to separate these compounds in heteroatom classes, like we can see here in these graphics. We have the distribution of OX compounds, O1, O2, O3, and also the N compounds. And we also have the information about the DBE and the carbon number. The DBE is the double bond equivalent, that it's linked to the hydrogen deficiency of the compound. So usually in petroleomics or in the result treating the data from the FT-ICR MS, we have this kind of graphics, the carbon number versus DBE. So you can see all the species from in this example, from the O1 class. So all the species with the specific carbon number and specific DBE. So this is only an overview, because what I want in this webinar is focus on the results from from that technique. So another point important that I will only give an overview is about the ionization. So for the electrospray ionization, it involves 3 steps. First, we have the dispersal of fine spray of charged droplets here. So then we have the solvent evaporation here, and then the ion injection from the highly charged droplet to the mass spectrometer. So in the electrospray ionization, you can have the positive mode or the negative mode. In the positive mode, you usually assess the basic compounds, but in the negative mode, you assess the negative compounds. So here is an example which compounds we can assess. And one important thing is to promote the deprotonation, we need to NH3 to the sample solution. This is important. So you can disprotonate the species. So what we can usually see in this kind of analysis using this kind of ionization is acid compounds such as naphthenic acids from O2 class, nitrogen acids from N1 class, and phenols from O1 class. This is the most that we normally see, but there are others, but this is the most usually in high abundance. So another important thing I think it's important to show is how great using the easy FT-ICR MS is to assess more compounds from petroleum. For example, if you have only the GCMS, it's possible only assess compounds with low molecular weight and low polarity. But if you have the FT-ICR MS, for example, using the negative mode electrospray ionization, you can assess more polar compounds and with high molecular weight. This is the reason why it's so important and significant, this kind of technique. So we can now assess compounds that before you couldn't assess. So in this webinar, I want to show two case of studies. The first of one is the evaluation, the assessment of the paleoenvironment of the Irati Black Shales from the Paraná Basin, Brazil. These samples are also source rocks for the petroleum that is in the Piramboia Formation, the very heavy oil that there is there in the tar sands Piramboia Formation. So these results are from my postdoc. I will talk about later. And the second case I would like to show you is this publication of Rocha and collaborators, 2018, about offshore Brazilian oils. They do a really, really interesting research investigating the paleoenvironment of the source rocks of these oils using the FT-ICR MS. I will present some results from them. So I will show some results from one source rock and another one for the oils. So the first is the Irati Black Shales that are the source rock, also source rocks for the tar sands of the Piramboia Formation. So this work was related to my postdoc at the GFZ in the 3.2 organic geochemical section. So I was supervised by Hans-Martin Schulz, and also I had the collaboration of the chemists there, Steffi Poets and Mahai Canoa, and also collaborators from Brazil. For this specific publication, we have the geologist Severiano Ribeiro and the chemist Georgiana Feitosa. So this paper was about new paleoenvironmental proxies for the Irati Black Shales based on acid NaSO compounds revealed by the ultra-high resolution mass spectrometry. So I will show you some results from this publication. But first, I would like to show you some previous works concerning the Irati Black Shales that give us the base to understand the samples, to understand the paleoenvironmental, and then we could go deep in the FT-ICR MS results. So here we have 4 interesting publications about the Irati Formation using mostly GCMS and inorganic techniques. So we have these 2 first publications on organic geochemistry about the paleoenvironment of the Irati Black Shales. Then we have this publication in the Journal of South American Earth Science. It's related to the master degree of the Maria Adriana. It's about the Irati Formation and its correlation with the Piramboia Formation. And the last one is this one in marine and petroleum geology that shows the changes in the positional paleoenvironmental of black shales. It's related to the PhD of the Carolina Dobson do Nascimento. So it's very interesting, and these publications give us the base to go very deep on the petroleomics results. So to talk a little bit about the samples, about the Irati formation, so it was deposited in the Permian in 278 million of years ago, as you can see here, in this geological timescale and lithostratigraphy. And here it's also showed the chemostratigraphy that was made by Hayes et al. 2018. And our samples, our black shales, Irati black shales, are part of the E and H sections, chemostratigraphy sections. So we have in this work, we work with 17 samples. 10 from the São Mateus do Sul area, here in the Central Eastern Basin, as you can see here. And we have also 10 samples from the Amaral Machado area, here in the Northeastern Basin, as you can see here in the geographical location. It's also important to say that these samples were collected from the base to the top of outcrops. So it's interesting because we can see how the paleoenvironment conditions change with this. So this is some of very interesting results, I think, from the first publication. Here we have the idea of the paleoenvironment that we reconstruct. So for the Amaral Machado, we have a more restricted, shallower marine. And for the São Mateus do Sul, we have more deeper marine with high productivity of the surface water. But both of the locations, we could see a stratified water column and also the presence of the photic zone euxenia. We took all this information from mostly biomarkers. If you are interested, you can check more details in the publications, because I don't have time now to detail these results, but it's pretty interesting. So we can see another interesting thing is there is also some influx of fresh water. We could see that mostly from the cromens, but also for others biomarkers. So this is how we believe was the paleoenvironment of the Irati of the Irati black shales. So now I will talk about more the FT-ICR MS result. I will start with the equipment that was used at the GFZ. It was a 12 Tesla FT-ICR MS equipped with Apollo 2 ESI source, both from Bruck-Daltonic, Germany. So this is the equipment. There is a picture from the website of the GFZ. And then I will start with the heteroatom class distribution, as you can see here. So we have here the distribution for the samples from the Amaral Machado area, and here the distribution of the samples from the São Mateus do Sul area. So here we have 10 Irati samples, and for Amaral Machado we have 7 Irati samples. In addition, we have 3 samples that is here in red that are from the Serra Alta formation. It's an overlaying formation of the Irati. I will explain a little bit about why we included this formation, these results in this work later. So what we can see here, and it's very interesting, is that there is some difference between the composition of the samples. As you can see here, for example, the O1 class diminish in direction of the top of the outcrops, and a lot of really interesting information here. But one that I want to highlight it is the high amount of the O more than 2 compounds here in the Serra Alta, shales. I will explain why this later. So, from another perspective, I would like to show the heteroatom classes, the variation in this profile, because here we can see better how the heteroatom classes change with the height of the outcrops. So what we can hear in the right side, it's the reconstruct paleoenvironment for the previous publications. So for example, here in Amaral Machado, at the base we have more marine hypersaline, and with the increasing flux of fresh water, it's in the top we have more normal marine with high terrestrial organic matter, and the Serra Alta shales here has a desoxy waters and a lot of a great terrestrial input of organic matter, and it's kind of similar for the São Mateus do Sul. So from the heteroatom classes variations, what it's interesting to show here is the high abundance of any one compounds due to the great algae input here to the base of the São Mateus do Sul. This is pretty interesting, this high abundance, because these first samples from the base, we could see from the biomarkers that there was a blue algal in this, a high amount of pristine and phytane, really, really high. So it's interesting that they also have high abundance of any one compounds. And also interesting, it's here from the base of the Amaral Machado, we have high abundance of SO compounds due to the harsh depositional conditions when archaea and marine red algae flourish in extreme sulfate-rich area. So here, as you can see, we have a high amount of SO compounds. These results are come from the first publications. And here from the Serra Alta, we have high amount of O compounds that indicate a high input of terrestrial organic matter deposited in oxy waters. So from these results, we could think that this variation could not be related only to the paleoenvironment conditions, but also, for example, from the maturity. So that's the reason I want to show these results also, that it's from the maturity of the Irati black shales. Here, in the left, in the right, in the left, we have the results from the Poets and Collaborators 2013, that they suggest this type of diagram using carbazoles, using benzocarbazoles, dibenzocarbazoles, and benzonaphthenocarbazoles to assess the maturity of rocks, of source rocks. So what we see when we check our samples, our Irati black shales, is that they are in the very immature area, as you can see here. If we compare these two graphics, we can see that our samples is in the area of 0.48 to 0.53 reflectance of Victor unit reflectance. So this is a very low maturity. So we can see here that our samples, the Irati black shales, don't have some difference in the thermal maturity, and also are very immature to only marginally mature. And this is in agreement with our other studies from the biomarkers and for the rock eval analysis. So I think the most interesting result for this publication is the 8 parameters that we suggest, as you can see in this figure. Here we have 9 because it's also showed 1 parameter from another publication. So we have all these parameters, for example, and they are basically based on the O1 class and O2 class. So from the O1 class, we have the phenol index and 2 parameters based on the isoprenodyl phenols. And for the O2 class, we have 3 parameters based on the fatty acids, the acyclic acids, and others 2 parameters based on the hopanoic and stearinoic acids. But how did we get these parameters? What they are coming from? I will show you how we achieve that. So I will start with the O1 class. So here we can see the distribution, the Dpi distribution of this class for the Amaral Machado area and for the São Mateus do Sul area. So it's interesting to see the high abundance of compounds with the Dbi-4 here and also the Dbi-5 here, mostly for the samples 23 and 24 at the top of these outcrops. So what we did is take this Dbi and obtained the carbon number distribution. So here we can see the carbon number distribution of O1 compounds with Dbi-4, and in the right we can see the O1, the carbon number distribution of O1 compounds with Dbi-5. What was really interesting is the high abundance of compounds with 27 and 28 carbons. This was really interesting for us. This could be the isoprenodyl phenols or some esterols. There are these 2 possibilities from the literature. So we want to be sure what kind of compounds were. So what we did was take the NaSO fraction of the Irritable shales and select it using the MS-TFA, prior GCMS analysis. And then we look for the isoprenodyl phenols selected, and we find it. So what we can see here is the mass chromatogram MZ 149, 194, 208, and 222, showing the distribution of the methyl and dimethyl isoprenodyl phenols as 3-methyl silyl ethers. So it was really interesting for us that we could be sure now that the isoprenodyl phenols are in the samples. They were detected in the samples. And another interesting thing was we did some correlation with the ratio between the 27 carbon over the 28 from the GCMS results with the results from the FT-ICR MS, and they correlated very well. For example, here for the sample, we have low ratios, and for the base sample, we have very high samples, like 1. And the same for the Amaral Machado. We have here high values, and in the base, the low values. So they correlated very, very well. So now we are more sure that these compounds are the isoprenodyl phenols. So from the O1 class, we suggested 3 parameters. The phenol index, that it's based on the percentage of Dbi-4 class, Dbi-4 compounds, and also 2 parameters based on the isoprenodyl phenols. So the C27 over the C28 for Dbi-4 and for the Dbi-5. So here is the profile for these parameters over the height of the outcrop. So what it's interesting to show here is for the phenol index, we can see high values for the top samples here that showing that is related to the highland plant input. And also pretty interesting, it's the high abundance here in the base of the São Mateus do Sul that we already saw in the others publication, a high influx of fresh water here with the algal bloom and probably a high land plant input. From the ratios based on the isoprenotyl phenols, it's really interesting here in the base that we can see here in the base of the Amaral Machado and São Mateus do Sul that they have high values that is related to the higher salinity. So with the increasing of the salinity, we also can see the increasing of these ratios. So they can be used to assess paleosalinity. It's pretty interesting. And other interesting result was the correlation between these two new parameters with the parameters using the methylchromase from the GCMS. So here we have the methylchromase over the G-methylchromase. So what we can see, it's a very good correlation. Not very good, but a good correlation between them. And here the methylchromates are usually high in samples normally deposited in high salinity environments. So with the increasing of this ratio, we have the increase in the salinity as for the suggested parameters. So we can see here a good correlation between them and that these parameters could be useful to assess paleosalinity. Now, I will talk a little bit about the O2 class. So here what we have in the left is the Dpi distribution of O2 compounds. So what we can see here is the high abundance of compounds with Dpi1 here, that are the fatty acids, as you can see here in the right. So, and also high abundance of compounds with DBF5 and 6. So this was some compounds that take our attention. So at first I will show the carbon number distribution of the DBF1 compounds, the fatty acids here. What we can see at first, it's very interesting, the profile with some odd over the even preference, so it's pretty interesting. And we can see also some high abundance of specific compounds, like here 24, 26, 28. So based on this distribution, we suggest 3 new parameters, and also take in account some parameters from the biomarkers. So we suggest here the even-odd fatty acid ratio and also the terrigenous echoes ratio for the fatty acids using the even and the odd acids, as you can see here. If you want to see more detailed, you can see in the publication how they are calculated in detail. So here you can see the profile of these 3 new parameters, these 3 parameters. So it's interesting to see for the terrigenous echoes ratio for the fatty acids, the high abundance, the high values for the samples at the top of the locations of the outcrops. This is probably due to the high land plant input. When we do the correlation of these new parameters with the parameters from the GCMS, the terrigenous echoes ratio from the hydrocarbons, we can see some kind of correlation. This was also really interesting for us. So for example, that samples for the top of the outcrops like 23, 25 or SM 3.7, 2.6 shows high values for both of the ratios. This was really interesting. And here you can also see high values for AMA1. AMA1 is in the base, is here, in the base of Amaral Machado. This is probably because this sample was deposited in a very proximal environment with more influx of terrestrial organic matter, land plants. So we believe it's the reason for these high values for this specific sample. So So only to remember that the regionals from this ratio is related to the long chain N-alkanoic acids like with 24, 26, and 28 carbons are the major components of the waxy coatings on land plants, leaves, flowers, and pollen. And the aquatic is related to the short chain with 12, 14, 16 carbon acids that are produced by all plants but are dominant lipid components of the algae. That's the reason these compounds were used to propose these parameters. And finally, we have here the carbon number distribution for the DBF5 compounds and also DBS6 compounds. So what was really interesting for us, it's the high abundance of these compounds with carbon number 20. Here, for example, carbon number 28, 29, 30, and also here for the compounds with carbon number 31, 32, 33. These compounds, these acids with the BF5 are mostly steranoic acids, but not only, but we believe are the steranoic acids, mostly these compounds in high abundance, and the acids with DB6 are mostly the hopanoic acids, mostly these compounds with high amounts. But of course, they can be also other type of acids like benzoic acid for the DBF5 or this kind of acid for DB6. But based on our results, these results, we suggest here 2 new parameters to assess the depositional environment. The first one is the C36 hopanoic acid index. This is related to the C35 homohopen index used to assess salinity and some reducing environmentals. Normally it's high to reducing environments. And also this hopanoic over the steranoic acids ratio to assess that it's related to the hopane over the histone ratio used using the biomarkers from the GCMS, since hopane is normally in high abundance in samples with a great contribution of bacteria. So we suggest these 2 parameters. Here I will show how they change in the profile with the height. So for the C36 hopanoic index, it's pretty interesting that we can see high values to the base of the 2 outcrops. For example, here in Amaro Machado, it's very high for the samples and also high for the São Mateus do Sul. This is probably related to the high salinity of the samples, mostly for the Amaro Machado. So we also did some correlation with other parameters, also from the GCMS. For example, in this first graph, we can see the correlation of these new parameters with the C35 homohopen index. There is some kind of correlation. It's pretty interesting. We can see that AMA1 and AMA5, there is samples from the base of Amaro Machado also have very high values of the C35 homohopen index. So we also did the correlation with the pre-10 over the FT-10, that low values are related to more anoxic conditions. So we can see here that AMA1 and AMA5 that has the high abundance, the high values for these new parameters, have also the low values of the pre-10 over FT-10, and these values are lower than 1. And also correlating with the abundance of the SO class, we can see that the samples from the base of Amaro Machado that have the higher values for this hopanoic acid index also have high abundance of the sulfur compounds. And then from the hopanoic steranoic acids ratio, We can see here in the São Mateus do Sul a very high values for these parameters, probably related to the high bacterial input. We also did the correlation between these parameters over the Hope and Stern index, and there is some also interesting correlation with the samples here from the São Mateus do Sul showing also high values for the Hope and Stern ratio. So far, this is what I want to show about these results by the Irati formation. And now I would like to talk also about this publication. It's using the offshore Brazilian, is investigating offshore Brazilian oils. It's by Rocha et al. And collaborators. Was published in 2018. Rocha is Igor from Petrobras. I think this publication is pretty interesting and is significant for the field that I'm presenting today. So the title is Geochemical Characterization of Lacustrine and Marine Oils from Offshore Brazilian Sedimentary Basins using negative ESI FT-ICR MS. So they investigate 69 oil samples from 4 different offshore Brazilian basins. 2 basins producing oils mostly from lacustrine origin, and the 2 others are known for the production of marine oils. So here in this table, you can see the basin A and basin D are lacustrine oils, mostly lacustrine oils, and basin B and basin C, they are mostly marine oils here. So this publication is pretty interesting because the authors want to show how the composition is linked to the origin, if marine or lacustrine of the oils. So I will show the main results from this publication. So this first result show the distribution of N, O, and NO classes here. It's pretty interesting that you can see that the marine oils have in general, high amount of O compounds, and lacustrine oils have high amount of N compounds, of nitrogen compounds. So this was pretty interesting. And I believe this high amount of nitrogen compounds from the lacustrine, it's because it's a high input of algae. So this was a pretty interesting result. And then here we can see the Dpi distribution for the O1 class for all the samples used in the work. We can see the high abundance of Dbi compounds of Dbi4 and 5 for the lacustrine oils than the marine. So this was also interesting. Dbi4 are mostly phenols that are possibly originate from land plants. So that it's a pretty interesting result. And also the Dbi distribution of the O2 class here. We can see the high relative abundance of compounds with Dbi1 that are the fatty acids in the lacustrine oils. So according to the authors, the high relative abundance of these fatty acids in lacustrine oils could be associated with the type 1 kerogen with a large amount of lipidic material containing aliphatic chains and low content of polyaromatic nuclei and heteroatomic bonds. And finally, I want to show this result. Here, they take some parameters based on the classes, the heteroatom classes, or Dbi classes. So they correlated these parameters and showed that the samples from the same origin correlated very well. For example, here, the samples from the basin A and D correlated very well and differently from the samples from the basin B and C. as for the other parameters that they show. So they showed that this composition, the polar NSO composition, could be related to the orange if marine or if Lacustrine. I think it's pretty interesting. So for now, it's that, the presentation. I would like to thank everybody that are here, the audience, to be here with me. I hope I could give some overview of this topic. Sometimes it's difficult because it's not my English is not my language, but I hope that you could understand at least a little bit about how important the NSO compounds could be to assess geochemical information from oils, mostly, especially in this webinar about the paleoenvironmental reconstruction. So thank you very much. Also, thank you again for the Alago committee, and a special thank to the 3.2 Organic Geochemistry section at the GFZ, where I did my postdoc from 2018 to 2019. So thanks for the colleagues and staff for all support. I had a really great time there. A special thank to Hans Martin Schulz, that was my supervisor. Here is a picture for our section trip to a coal mine. That was an incredible field. So I would like also to thank the Laboratory of Petroleum Geochemistry from the UENF, where I work. So thanks for the colleagues, for all support, and also the contribution to the present work about data information, especially to Eliane, Professor Eliane, and also the Dr. Caroline, and also Professor Georgiana, and all colleagues there for the great support. Is that?
Thanks, Laercio, for the wonderful talk, very interesting topic, and showing the powerful of the FT-ICR technique into the paleo-environmental history of shale and also the crude oil samples. You have here some of questions. First of all, I have one of mine, and that because this is so interesting. And will you show us that on ternary diagram using the as an oxygen containing compounds profile that you could separate the families of oils based on the paleo environment. Did you try do APPI to do this analysis? Because as you show us that S containing compounds may be the 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 key to separate this trend.
Yes, actually, we did the APPI analysis, but we didn't publish yet. But we have some interest results from that, and we will show. Excuse me, Bonnie, you told about the sulfur compounds? I mean,
Yes, yeah, because you show us that S and oxygen compounds, but for electrospray ionization, you don't access just S compound, S concentration
yes.
only.
Yes, the results from the PPI are very interesting also, and of course the sulfur compounds that we can measure there. So it's interesting, and there are a lot of difference between the samples. For example, the samples from the Amaral Machado in the base, we have a very restricted environment. So it's pretty interesting to assess the sulfur compounds, the organic sulfur compounds. So we already saw that in the PPI, and we will show the results. Not so will not take so much time.
Yeah, this work is so nice and very complete in terms of assessment. You focus on the non-polar and polar compounds. You show us some ratios. For example, the hopanoic and steranoic acids. This rate was did using the FT-ICR data or the CMS data?
The ratios, the hopanoic and seranoic are from the FT-ICR MS results.
Okay,
Yes. We suggest that we still want to check these results using the GCMS from the NSO, as we did for the isopropanol, but we didn't yet. But it's something interesting to prove uh, if these compounds are really the hopanoids and steranoids. Yeah,
yeah.
I understand. I think it's interesting. But as you know, I did a lot during the postdoc. It was a lot of information. So I saw some things that I can do, but it was not possible at the time. But now I can work with that. And these are something that I want to do. Check the hopanoic and seranoic using the GCMS.
Okay, nice, very nice. Here you have a comment from George Orego. I think it's from in the follow manuscript, George Orego, Energy Fields 2020. The parameter DBE4, DBE5 for O1 class proposed by you in 2017 was rated as indicator of depositional environmental in samples with low and no biodegradation. It would be great if this parameter is validated for this kind of samples. Since in the work of Martins, this was proposed as biodegradation parameter. Additionally, in this manuscript, a positive a a positive correlation between the relative abundance of oxygen-containing classes O1, 2, and O2, well, oxygen 1 and oxygen 2, and the ratio Pristan and Fitan was established. This correlation allowed for the observation that samples with a high oxygen content, either O1 and O2 classes, showed high uh, Pristan and Fitan and vice versa. In the same work, the C27 by C29 dB41 ratio was useful for classifying the samples according to the reservoir from which the oils were produced as potential indicator of origin. Unfortunately, this work was not cited in this work. Okay, and in any case, the results and the interpretation presented by Dr. Martin's group were very interesting and show a significant advance in the geochemistry and NSO compounds. Congratulations.
Yes, I will check the publication that you're talking about. I don't remember now, but I will check it. Yeah.
Okay. Now you have another question from Hossein from Calgary. Thanks, Laercio. I would like to know your opinion about the relationship between the concentrations of the isoprenyl phenols in oils and the lithophase of their source rocks.
Yes, I believe the isoprenophenols could be more in high abundance in lacustrine, in rocks deposited in lacustrine depositional environment. I believe this could be some relationship, the abundance of the isoprenophenols. I didn't I didn't do this in this publication from the Irati formation, but I did using some oils, and we already could see some correlation, more lacustrine, more abundance of this type of compounds. So it could be related to lacustrine lithophase.
Okay. Now we have one more question from Daniele Mitzer, UFG. Hi, Laercio. Congratulations to our presentation. I have one question about the thermal evolution of the sample of Irati that you show in the slide 14. The samples were the same origin.
Yes, they are. All the samples are from the Irati formation. They are from different locations. We have 7 samples from the Amaral Machado and 10 samples from the São Mateus do Sul area. But all they are from the eruptive formation. And it's pretty interesting that the FT-ICR MS results confirm that they are really, really immature, as we already know that the eruptive formation are very immature. And on the other side, we can see that the diagram already suggested by others research, it works. It works very well for the eruptive formation. So, but it's the same order.
Now the next question is from Marcelo. It's from Federal Fluminense University. How about maturity effects? Could those analyses be more precise than vitrinate reflectance and help to better evaluate the production potential?
Yes. How about the maturity effects? Actually, in this work, that's the reason I wanted to show that result from the maturity, to show that all the samples are very low, immature, and we unfortunately couldn't do the vitrinite reflectance. Unfortunately, it's one thing that I wanted to do, but the geologists say that was not possible because some features of the samples, so we didn't. And to help to better evaluate the production potential is the thing is in my research at the GFZ, I was not focused in the potential, the petroleum production potential of the samples. I was more concerned about the paleoenvironmental conditions, and so that's the reason I didn't go so deep in these things like the production potential. But and help to better. That's the reason I think this last part I don't know, but I think it can help because you can check the maturity by the FT-ICR MS, so we can also have an idea of the production potential.
The next one is from Tamara Barra from Federal University of Rio de Janeiro. The ternary diagrams to access maturation cannot be also with DBs 9, 12, and 15 besides 12, 15, 18. Would you suggest one or the other depend on the maturation level of the samples?
I think the better idea is to do both. I did both. They both didn't show it great variation. I I decided to show the diagram using the 12, 15, and 18 because it's come from an publication that show that work with source rocks, with rocks, because the others that show that suggested using the DBN 9, 12, and 15 was using oils. That's the reason I choose to show this one, but I don't know. I think the most appropriate is check both of the diagrams to see how the nitrogen compounds will will change with the maturity. I really don't have any other answer now. Yeah, maybe for more immature samples, more mature samples, maybe it's interesting to show the DBA 12, 15, and 18. And maybe because of that, you did this question. But I think it's important to check both of the diagrams.
Okay. Now the last one question is from Janderson from Federal University of Pernambuco. How did you calculate the FT-ICR ratios from relative or absolute abundance of ions?
From relative abundance of ions. Yeah.
Okay. Laercio, one more time, thank you for the wonderful talk and the wonderful talk today. And now I invite everyone here to the next Alago webinar that will be present next Tuesday in the about analytical geochemistry. And I hope see you uh, all in this webinar. Thank you and have a good night. Bye.
Thank you very much. Bye bye.